Thanks to Brilliant for helping support this episode. Hey Crazies, you've probably heard of white dwarfs, black dwarfs, and red dwarfs. They're all types of stars, or at least the remnants of stars. But there are also these strange objects out there called brown dwarfs. They're a little big for a planet, but a little small for a star. So which category do they fall into? Planets or stars? Are they actually brown? What are they made of? Here's everything you need to know about brown dwarfs. Full disclosure, brown dwarfs are a relatively new object of interest for astronomers. They were first hypothesized in 1962, but we didn't discover one until 1988, and that wasn't confirmed until 1995. So the study of brown dwarfs is only like 10 years old. What? I would do that math again. 2023 minus 1995, borrow the one. Oh God, that was 28 years ago. Still though, it's still very recent for astronomy. We discovered black holes first. Not only are brown dwarfs very dim and very small, most of the light they're emitting is in the infrared range. Thankfully, humans are really good at solving problems. When we want to. Our infrared telescopes have allowed us to find over 3,000 brown dwarfs. This image was taken with the Very Large Telescope in Chile in 2004. Is it orbiting that white star right there? Oh, no, that's the brown dwarf. Then what's the reddish brown thing? An exoplanet orbiting the brown dwarf. This is the first picture ever taken of an exoplanet. We had to overexpose the image to see the exoplanet, so the brown dwarf looks white. So they're actually brown? Well, no. Stars come in many colors, and we can sort them by surface temperature. You'll find brown dwarfs over here below the red dwarfs. They're like sub-red dwarfs. Of course, brown isn't dark red, it's dark orange. It would have made more sense to call them crimson dwarfs. But I don't get to name things, okay? Don't at me. These brown dwarfs would be mostly a deep red color. But depending on how you see color, it might come across a bit magenta. That's just the really hot ones though. The cooler ones would actually be black, only becoming visible due to reflection, like planets. And they wouldn't be much larger than a planet either. The largest planet in our solar system is Jupiter. It's about 11 Earths across and contains almost 318 Earths worth of mass. But if you add any more mass to Jupiter, it wouldn't get much bigger. It would just get denser. So the next time you hear about some exoplanet that has the mass of 10 Jupiters, yeah, that looks like this. All objects in this mass range have roughly the same volume. Brown dwarfs start at about 13 Jupiter masses and go up to about 80 Jupiter masses. But they're all about the same size. You don't see any dramatic size differences until you start looking at actual stars. Are brown dwarfs stars? No, they're substars. You mean like planets? Also no. On the mass scale, they're sandwiched between planets and stars. They're like the cosmic middle child. Properties of both, but belonging to neither. Classification is difficult work, but we do eventually figure the shirt out. Did I hear someone say shirt? No, I said shirt. Shirt. Science Asylum merch is always available, just like this awesome We Need Better nonsense shirt. Link in the doobly-doo. Unbelievable. Stars have an incredible amount of mass. I mean, our sun has a mass of 333,000 Earths. That's a lot of mass. Without nuclear fusion, stars would collapse in on themselves. Inward gravity raises the temperature of the stellar core. The fusion from that core provides an outward counterforce to balance it. But the less massive the star, the lower the gravity, which means the lower the temperature, which means less outward force from fusion. So lower mass stars find equilibrium at a smaller size. But there's a limit. Long-term sustained hydrogen fusion isn't possible below a certain temperature, somewhere around 1.6 million Kelvin, which sure is incredibly hot by human standards. But for some perspective, our own sun's core is 10 times hotter than that. Anyway, a core temperature of 1.6 million Kelvin corresponds to a surface temperature of about 2,000 or 3,000 Kelvin, and a mass of about 8% our own sun's mass. That's equivalent to the 80 Jupiters we mentioned earlier. All objects above this limit are considered stars and can be plotted on an HR diagram. For anyone new to these diagrams, they're nothing fancy. It's just brightness graphed against surface temperature, aka surface color. Our sun is right smack in the middle. It's a small white star. Aside from allowing our existence, it's fairly unremarkable. It's currently in a region of this graph called the main sequence. All stars in this region are primarily fueled by sustained hydrogen fusion, and they'll be here for most of their lives. But if we look at lower mass stars, we can see they're dimmer and cooler. Eventually, we get down to the red dwarfs. They're the coolest stars. They could sit on the main sequence for trillions of years. Brown dwarfs are below that. If we go cooler than red dwarfs, we step off the main sequence. None of the objects down here can sustain hydrogen fusion, at least long term. Brown dwarfs are essentially failed stars. You mean like Jupiter? Absolutely not. I'm so tired of this myth. Yes, Jupiter is incredibly massive. It contains half the mass orbiting the sun. But don't let anyone convince you it's a failed star. Jupiter is not a failed star. Brown dwarfs are failed stars. Jupiter is definitely a planet. The distinction at low masses might be vague, but Jupiter is nowhere near that boundary. While the upper bound for brown dwarfs is clearly defined by hydrogen fusion, the lower bound is a bit undecided. Oh man, do I really want to bring up this internet discourse again? Okay, the official definition for all astronomical words is decided by the International Astronomical Union, or IAU. They've been around since 1919, but they rose to infamy in 2006 because of the Pluto decision. We're not going to get into that today. That decision was for the lower bound on what it means to be a planet. We're looking for the upper bound. The IAU has a definition for this too, but it's messy at best. It's just a placeholder, it was never meant to be the final answer. So let's start by taking a look at how stars and planets form. It all begins as a giant cloud of cold gas and dust. Both planets and stars will form from this cloud, but in very different ways. Stars form quickly from the gas and dust itself, usually near the center of the cloud. This consumes the vast majority of the cloud's mass. All the leftovers form into small rocks first. Those rocks then very gradually combine to form things like planets. It takes hundreds of millions of years longer. Even gas giants like Jupiter form this way. There's a rocky core somewhere in there. That's the distinction I think makes the most sense. Brown dwarfs should be defined as objects that form like stars, but aren't massive enough to become stars. If it forms like a planet, then it's a planet. Simple, distinct, and clear. Unfortunately, we don't have direct access to formation history without a time machine. And the last time I used one of those, things went very badly. We don't even know if each brown dwarf formed in the star system we found it in, or if it formed by itself and was captured later, or if it was ejected from some other star system. So while my preference makes the most sense theoretically, it's probably not that useful to astronomers. I'm guessing that's why the IAU definition hasn't been updated since the mid-aughts, or as the Brits would apparently say, the mid-noughties. Anyway, let's go through that IAU definition. Item number 1, objects with true masses below the limiting mass for thermonuclear fusion of deuterium, currently calculated to be 13 Jupiter masses for objects of solar metallicity, that orbit stars or stellar remnants are planets, no matter how they formed. Jargon alert, jargon alert, jargon alert. I'm gonna explain it, calm down. Deuterium is just the fancy name for heavy hydrogen. That's hydrogen with an extra neutron. Fusing deuterium is a lot easier because it requires one less step. To be clear, fusion always requires that we overcome the natural repulsion of atomic nuclei. That can be done either with ungodly temperatures or through quantum tunneling. Ideally both. But with regular hydrogen, that's still not enough. To make it stick, we also need a weak interaction that turns one of the protons into a neutron. Otherwise, they'll just push themselves apart again. Deuterium doesn't require that extra weak interaction, so it fuses at a lower temperature. Temperatures you might find in a substellar object like brown dwarfs. Side note, technically, deuterium fusion happens in all stars before they get to the main sequence. You know, before they're hot enough for hydrogen fusion. Brown dwarfs just don't ever make it to the main sequence. End of side note. All right, back to the working definition. Item number 1 says objects below 13 Jupiter masses are definitely planets because they can't fuse deuterium. Item number 2 says any substellar objects above 13 Jupiter masses are definitely brown dwarfs. It doesn't matter how or where the object formed. How is that messy? Sure, it sounds simple and clean until you try to categorize objects. Say you've got two objects with a mass of, 20 Jupiters. By the IAU definition, these are both clearly brown dwarfs. But then we look a little closer and notice quite a few differences. Maybe this one has a rocky core and behaves more like a gas giant planet. Some brown dwarf spectra match up quite well with gas giants. But maybe this other one behaves more like a star. It's gas or plasma all the way down. In that case, calling them both brown dwarfs doesn't really tell us much about them. The only thing they have in common is their mass. It could just be that brown dwarf is too broad a category to be useful. These objects actually span 3 spectral classes on the HR diagram, L, T, and Y. The L-class dwarves are the hottest, so they're mostly plasma. The T-class dwarves are a little cooler, so they'd likely be a mix of plasma and gas. The Y-class dwarves are the coolest, so they'd be mostly gas. Assuming they all form like stars, they'll all start the same way, as a protostar. They'll fuse deuterium into helium during the initial collapse. But that deuterium supply will run out after several million years or so. After that, it will collapse further in an attempt to become a star. But alas, there's not enough mass. Mechanical forces can halt the collapse before it gets hot enough, kind of like gas giants. The brown dwarf will eventually settle, and its appearance will depend on its temperature. With such a low mass and no fusion to speak of, these objects are immortal. Full-blown stars become black holes, neutron stars, or white dwarfs. They end as stellar remnants. Brown dwarfs will be brown dwarfs. Forever. Forever. Well, unless they get eaten by a more massive object at some point during their lives. If left to their own devices, though, they will cool off over time. So the spectral class depends on more than just mass. Each Y-class dwarf might be young with a lower mass, or it could be old with a higher mass. We have to measure the mass separately to know for sure. Some of them are so cold that there's talk of adding a 4th spectral class, Z-class dwarfs. But that's a problem for data-driven astronomers. We'll let them figure that one out. In simplest terms, brown dwarfs are just substellar objects. Too cool to have any long-term fusion reactions, but hot enough that there might be a few short-term ones. If the brown dwarf is still fresh enough to shine, it might appear a deep red color. But its thermal spectrum will actually peak in the infrared. We've been able to find thousands of these objects so far. And thanks to some citizen science, thousands more have been identified for review. Even JWST is on the job now. In the end though, brown dwarf might just be a temporary name. Classification is one of my favorite parts of science, but it's difficult to do. Us humans, we need to split reality into metaphorical boxes to understand it. But the universe resists. True reality has no lines, no boundaries. It just is. And until next time, remember, it's okay to be a little crazy. If you want to understand reality a bit better, Brilliant.org is a great way to do just that. YouTube may be interactive through the comments section, especially on my channel, but if you really want to understand this stuff, you need to do it yourself. Brilliant has thousands of interactive lessons on many different topics, from the fundamentals of science all the way up to advanced mathematics. And they add new content monthly. You might pop over there to check out their astrophysics course, but once you're there, you'll have access to their entire library of courses. You can even learn practical skills like how to make neural networks or do data science. Brilliant's content is interactive, providing feedback and helping you understand the why. And I'm a huge fan of why questions. So if you want to try Brilliant for free for 30 days, visit brilliant.org/science asylum or click the link in the description below. The first 200 of you will get 20% off Brilliant's annual premium subscription. It'll also let Brilliant know you heard about them from me, which helps out the channel. Many of you pointed out the complex nature of Schrödinger's equation. Sure, as long as the time component is a complex exponential, the solutions will be wave-like. But that motion is in the complex plane, it's not real. When you take the complex square to get probability density, the wave motion disappears. Anyway, thanks for watching.